Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'll show CFD analysis and parametric study of a heat pipe using SolidWorks flow simulation. This heat pipe is actually made up of copper, and you already know that the effective thermal resistance of copper heat pipe is very less compared to normal copper. In a reverse way, you can say that thermal conductivity of heat pipe is very high compared to normal copper, maybe at least 10 times more depending on different specifications and different material inside. Now heat pipes, it may be of different types. What is there inside these heat pipes? Actually some kind of wicks are provided, and if we are providing heat from the bottom source, it will be evaporated and it will flow from down to top, and again it will come back from top to down. Because of capillary action, it will come back from top to down again. For better understanding, let us cut the heat pipe from middle section and show how it will be working. Let's cut it from specific plane. Yeah, we are cutting from top plane. See here, we have provided some kind of a specific section inside. So from the bottom part, when we will be providing heat, it will flow. Very little amount of liquid will be there inside this heat pipe. We are providing very little amount of water. This heat pipe is actually consisting of three different sections known as, this is bottom portion is known as evaporator part, the middle portion is known as adiabatic part, and the top part is known as condenser part. So initially we will provide heat at the evaporative part. Down part little amount of water will be there. As it is getting heated, so it will be evaporated and will be passing from bottom part to the upper part. And after going to the upper part, it will come back from these spaces. So it will be continuous flow of fluid from down to top, and again from top to bottom it will be coming again and again. So the heat pipe seat is having a specific type of advantages. That means its thermal conductivity is very high compared to normal copper, right? We can say that its effective thermal resistance is very less compared to normal copper. Through this analysis, we'll try to show the effectiveness of this one, and also we'll try to see the temperature difference at different cross-sectional areas or different sections of evaporative part, condenser part, and also adiabatic part. And again, we'll see its effectiveness at different orientations, because if we change the orientation of this heat pipe at different angles, its effectiveness will be changed. We will try to optimize its effectiveness using this CFD analysis. Okay, so let us start this one. Okay, so flow simulation environment will be initiated with flow simulation, and from the wizard itself we can initiate this one. The default name of the project we are keeping as project 4. Next to that, we have to select what type of analysis it is. It is an internal analysis definitely, and we are unchecking the condition of exclude cavities without flow conditions, because inside this one flow conditions will be there, and definitely it will be from physical features. We can select it is heat conduction in solids, and gravity will be definitely involved, because as height is changing, heated fluid has a tendency to go up because of gravitation effect, and the direction of gravity will be y. So along y direction it will be minus 9.81 meter per second square, and along z direction it will be 0. Next to that, we have to select that fluid. Default fluid inside this heat pipe will be water, and very little amount of water will be inside. Next to that, we have to select the different materials. Initially, we'll select the default material for this heat pipe will be made up of copper, that will come from metals, and the other materials will be provided during application of boundary conditions. Default out-of-wall thermal conditions and roughness we are considering. Next to that, thermodynamic parameters. It will be, let us change the parameters of pressure and temperature also. So let us go back and we can change the temperature and pressure units. We consider pressure unit to be bar and temperature unit to be degrees Celsius. So atmospheric pressure will be 1.01325 bar and temperature will be 20 degrees centigrade. and solid parameters also it will be having same temperature. It will be 20 degrees centigrade. Let us finish this. You can see this is the computational domain. Let us hide the computational domain. Done. Fluid subdomains. It is having only one fluid. It is not necessary to provide fluid subdomain, but for your understanding, we'll provide a fluid subdomain. Inside fluid subdomain, it will be having water inside this copper tube, and it will be water at a very low pressure. It will be at a pressure of 0.4 bar. Done. Next to that, we have to apply different conditions. Initially, we'll provide the heat surface. Before that, we can provide these materials. Let us provide materials. Solid materials. Predefined. It will be metals. And from metals, we can select copper as a default material for this heat pipe. We can select from the solid bodies, adiabatic zone, evaporator zone, and even the condenser part. All are made up of copper, right? So we will select this one. Copper is selected for the main body. Next to that, we have to provide different materials for the heat source and also the cooling part. Here we are providing some fins at the condenser part. Solid materials, insert solid materials, predefined alloys. It will be aluminum 6061 alloys for the fins, which is provided at the condenser part. Grain check is done. Next to that, we have to provide another material at the heat source. Solid materials, insert solid material, predefined. It will be definitely metals. We can provide titanium for the heat surface. You should not be having any problem while getting heated. We have provided titanium at the heating surface. Grain check. All the materials have been provided. Next to that, we have to provide boundary conditions and initial condition, right? Starting from conditions, and initially we have to provide a heat surface, which will be providing heat at a rate of 25 joules per second or 25 watt. So we can select that heat surface or surface source. This one will be providing heat at a rate of 25 joules per second or 25 watt. Grain check. Next to that, we have to provide the heat pipe, right? Okay, so from conditions, you can select heat pipe, and initially we have to select all the component of the heat pipe that can be selected from the solid bodies. You can select adiabatic zone, evaporator zone, and also condenser zone. So all the heat pipe is selected. The next section, you have to select that heating surface. It will be from here. Heating surface is selected at phase 1, and finally we have to select that cooling zone. That means that condenser part where we have provided some kind of fins. Let us select that one. It is selected. Phase 2. Next to that, effective thermal resistance, and this is actually one experimental property. This value will be 0.02. Grain check. We can do one thing, like we can provide some kind of convective heat transfer coefficient at the surface of these fins. That can be provided, but for having the process to be simplified, we are not going for these things. It can be done later on. Okay, next we have to provide some kind of goals. Insert surface goals. We want to have temperature of fluid. That means we want to have average temperature of fluid at different sections of this heat pipe. Let us select the sections. We'll take a cross-sectional view of this one, and we have to have goal ports at different regions, right? So goals, insert surface goals. We want to have average temperature of fluid at different locations, right? Let us select here. That is at the evaporator zone. Second, we are selecting here. That is the adiabatic zone. And third one, we have to select at the condenser zone. At specific locations we are selecting, and we have to create goals for each surface separately. Let us select this one. So we have provided 3 different goals. This is the first one, is the average temperature fluid at the evaporator zone. So we can select this one as evaporator. We can rename this as average temperature of fluid at evaporator. Second one, we can rename that average temperature of fluid at adiabatic zone. And the last one will be average temperature of fluid at condenser zone. Done. We have selected all the goals. Next to that, we have to run the simulation with new calculations. Iterations have already been started. Mesh refining is going on. We'll see the results from the SolidWorks window itself. You can see the goal plots from here. By the same time, you can select the actual views of these things. You can see average temperature of fluid at adiabatic zone is 20 degrees centigrade. Actually, it is having high thermal conductivity, so the temperature difference at different zones will be very similar. It will be very less difference will be there. You can see the actual views from front plane. Settings, instead of pressure, we want to select temperature of fluid, and image attributes, we want to see 2000 by 2000 with a rotation 90 degree. So this is the heat pipe. You can see how the temperature will be varying from one end to another end. See, at the bottom part, temperature is very high, which is indicated by the color zone. It is yellow zone, that means temperature is high, and green zone it is moderate, and blue is minimum one. You can see this one in between. If we drag this one a little bit, we can see how temperature is varying from bottom part to top part. You can see this. So this is showing the temperature distribution from bottom to top through the heat pipe. So inside this heat pipe, very little amount of water is there. As at the evaporator part, we are providing heat at a rate of 25 joules per second. So water is being heated up, and finally after being heated, it is being evaporated, and it is being transferred from this evaporator part to condenser part. Okay, let the iterations move on. Whenever it is finished, we will see the results and go for detailed analysis. Okay, solver is already finished. Now you can see the results from different cut plots and goal plots. For viewing the dynamics of flow particles, let us make the model transparent. So model is transparent right now. Now you can see the different goal plots and the cut plots from the results itself, right? You can go it from here. Let us see the results from here. Initially, we see the cut force of temperature of fluid from front plane. Insert cut plot. You want to see all these things from front plane. Instead of pressure, we want to see temperature of fluid. Grand check. Let us see temperature of fluid distribution. At the bottom part, its color is red, which is indicating that temperature at the bottom part is in the range of 108 degrees centigrade, and as it is approaching towards the end part, its temperature is reducing, and the middle portion is temperature is moderate, which is indicated by blue color, light blue or sky blue. It is 106 degrees centigrade, and at the top part, its temperature is less. It is in the range of 105 degrees centigrade, right? So what we'll do is we can see this one in the form of an animation, right? Let us see this one in the form of an animation. Cut plot 1. Let us play. Let us see the animated view of this temperature distribution along front plane. Okay. Let us clear and hide these things. Next to that, we want to see surface plots also across the external surface of this heat pipe. Surface plots. Insert surface plots. We want to have temperature of fluid across all faces. So we select all faces and grand check. It is showing at different surfaces temperature is different, as it is clearly understood that in the evaporator zone, the temperature of the surface is indicated by red color, which is 108.39 degrees centigrade, and in the middle section, which is a combination of different types, little bit of red and little bit of yellow, which indicates it is having mid-range temperature. And at the condenser zone, you can see in the range of 106 to 105 degrees centigrade, right? So these are the temperature distribution which is seen across the boundaries and the surfaces only. Next to that, we want to see the very important part, that is flow of fluid from the bottom part to the top part in the form of flow trajectories. So to see this one, first of all, we have to make this part hidden, surface spots clear and hide these things. And next to that, we want to see the most important part, that means flow trajectories. Flow trajectories, insert, instead of 20 numbers, we want to make it little less. Maybe let us see 10 numbers of flow particles. We want to see from this heat pipe the size of these particles. We have to make it smaller. Let it be 0.305 meter. And instead of pipes, you want to see all these flow particles in the form of arrows only. Let us select that location. From the bottom part, we want to see the dynamics of flow particles. Let's make it a segmented view and we can select a specific location better way. Okay, let us select that location. From here, we want to see the dynamics of flow particles from bottom to top part. Phase 1 is selected. Grade check. It will take huge amount of time for getting this particle study to be generated. It is done. Now you can see the dynamics of flow particles through this heat pipe. It is very clumsy. You can see that lot of particles are going up. At the bottom part, you can see here temperature is very high and some particles are going down from top to down. So it is clearly understood that lot of particles are going up, and when it is heated from the top part by capillary action, it is moving down again through that heat pipe. Okay, so mixed flow is possible here. As you can see, continuous flow of heat is possible. Initially it is moving from bottom to top, and again from top to bottom by capillary action it is coming down, right? So you can see this one in the form of animation also. Let us try to show that dynamics of flow particles in the form of animation. Flow trajectories. Let us play. You can see some particles are going up and some particles are coming down. So there is a mixed flow inside this heat pipe, right? There. Okay. Next to that, we will see the goal plots, and we'll try to go for optimization based on different orientation of this heat pipe. Okay. Let us see the goal plots from here. Insert goal plots. We have to select all the goals, and let us see. We can export this one to Excel also. Let us see from here itself. Let us show all the goal plots. These things we have already seen from the solver window. It is better to see these things in the form of a graph, which can be obtained from history. Let's see these things. Initially, the temperature of fluid, you can see average temperature of fluid at the evaporator zone. It is the highest temperature zone. Initially, its temperature was near about 20 degrees centigrade, and you can see the final temperature at the evaporator zone is 106.85 degrees centigrade. So total numbers of iterations equal to, in this case, 27, and temperature after 27 numbers of iterations, it is 108.32 degrees centigrade. Similarly, for the fluid at the adapted zone, after 27 numbers of iterations, its final temperature is 107.76 degrees centigrade. And finally, at the condenser zone, its temperature will be a little less, is 106.65 degrees centigrade. You can see here the difference between the evaporator zone and the condenser zone temperature is very less, right? It is 106 at the condenser zone, and at the evaporator zone, let me see how much it is. It is 107 degrees centigrade. So the temperature difference is only 1 degree centigrade, right? Next to that, we have to go for some kind of optimization based on its orientation, right? We'll go for optimization from here. Solve new parametric study, and from here we'll select design of experiments and optimization. And for this design of experience and optimization, we have to depend on input variables. Input variables may be obtained from the different boundary conditions, or it may be obtained from the geometry itself. We are trying to have the dimension to be constant, and in this case we will try to change the orientation of this heat pipe. So we have to depend on that geometrical part of this heat pipe. You can select the geometries from here. For getting the geometries, go back to the model again. This is the model, this is the angle. We can set the angle to be the input variable. We'll change the orientation of this one. Initially the angle is 90 degree. The angle is provided in the form of radians. We have to change different angles, right? Let us change these values from 0 degree to 90 degree. 90 degree is equal to 1.57 radian. We'll change this one from 0 radian to 1.57 radian. That means 0 to 90 degree. Go and check. Let us see the output parameters. And it is dependent on goals. You can select all the goals. We're going to have the temperature at different levels, at different orientation, right? Let us see the scenarios. We are setting 5 numbers of different experiments. Let us create those goals with different 5 orientations, right? So we'll select this one at different orientations. You can see that radians can be converted into degrees also. Let us run this one. Iterations have already started. At the different orientation of the heat pipe, we'll see the different goal plots. Let the iterations move on. Whenever it is finished, we'll see the results and see at what orientation, what are the results available and which one is the optimum one, right? Parametric study optimization results is obtained. From this data obtained, we can see that at different angles, different values are there at different angular orientations. First one is 1.17 radian, that is approximately equal to 67 degree. Second one is 0.392 radian, which is equal to 22 degree. Third one is 1.57, which is approximately 90 degrees. Fourth one is 0.785, which is equal to approximately 45 degree. And the last one is 0 degree. From this data, it is evident that maximum temperature at different ranges when the angular orientation is 22 and 45 degree. So the optimum results can be obtained in between 22 degree and 45 degree, right? So in 22 degree, it is having better results, of course. If the temperature at the evaporator is 103.54, and when it is 45 degree, it is 103.31. Similarly, the temperature at the adaptive zone when the angle is 22 degree, it is 102.99, and when the angle is 45 degree, it is 102.75. And finally, when the orientation is 22 degree, the temperature at the condenser zone is 102.67, and the same with the orientation of 45 degrees, 102.43. So it is clearly evident that to have a maximum efficiency or optimum temperature, we have to select the orientation of the heat pipe to be in between 22 and 45 degree. Okay, this is all about our today's analysis. In this analysis, we got the temperature at different zones of heat pipe, that is the temperature at the condenser zone, evaporator zone and adaptive zone. It is having high thermal conductivity compared to normal pipes. So in the reverse way, you can say that the effective thermal resistance of heat pipe is very less compared to normal copper. So it will be working as a very good thermal conductor. And again, to have better efficiency, we can change the orientation of this heat pipe. When the orientation is in between 22 to 45 degree, in that case we can have maximum temperature at different surfaces of condenser, evaporator and adaptive zone. Okay, thank you all of you for watching this video. Thank you again. Bye. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.